Hello and welcome to Beamer Folk. What you see before you is another one of my bird's nests on a breadboard, is my implementation of an arbitrary wave generator. This is a bit of a bargain basement variety and it has its limitations. But before I go into the fine details of this, and I've got a circuit diagram, etc., but before I go into that, let's go off and just see a couple of waveforms that it can produce. And this is by no means limited to the ones you're about to see, but it gives an example of what can be achieved. Okay, this is a trace of a triangular wave. You can see that it has 8 steps on positive going and 8 steps on negative going. They're equidistant in both voltage and time, and so this would probably be quite useful for checking the linearity of, let's say, an audio amplifier. If you pass this through a low pass filter or integrate it, you will get a trace that looks like this, and the integration is done on the output op amps. Incidentally, an arbitrary generator can get very sophisticated and expensive indeed. You can even get an arbitrary wave generator that is in software on your PC, and the output comes out via your PC. And with one of these arbitrary generators, you can actually trace the waveform that you desire, either in a continuous form or a single shot. So my arbitrary generator here is nowhere near that. I'll move to the next one, and here's another trace. This is a trace of a sine wave, again done in steps, and you can see that the greatest steps are going through 0, which is the greatest rate of change. Move on to the next one. This is an integrated version of what you just saw, and it's effectively put through a low pass filter. And you can see it's slightly notchy. You can improve upon that by increasing the capacitor on the integrator. But if you increase it too much, although the quality of the sine wave improves, the amplitude of the sine wave will reduce. On to the next trace, and this is a square wave trace, and it is at the same frequency as the frequency of the sine wave or triangular wave. These little glitches that you can see on the top and bottom can be removed by putting a very small amount of capacitance on the integrator. Move on to the next one, and this is an integrated version of the square wave you just saw. Incidentally, the capacitance that I use on the integrator for this was, you can experiment with any value really, but the one that I used was 820 puff. And you can see this is a classical exponential rise, exponential drop, typical sort of RC waveform from a square wave. And this is if you like, an odd wave 1, where you can see you've got notches going down, notches going up, quite castellated really. And when that's integrated, it looks like this, which is a very rough looking sine wave. But you can see from the previous trace to this trace how a strangest sine wave can be built from those square wave pulses. Move on to the next one. This is interesting. It gives the suggestion of a differentiated waveform, and when we pass that through the low pass filter, the integrator, see how it looks. This is on the next trace, and there we are. This is a rather classic waveform that's been synthesized by this little oscillator that I've built, and it demonstrates quite clearly a differentiated waveform. It's as though you've put a square wave through a capacitor. This can be used for many applications and is a very classic trace. And there we are. You can generate many traces with this, many permutation traces with this little circuit. All you have to do is change the resistors, or put a diode in, or remove resistors, or change values of resistors. Of course, it's not as easy as, say, varying a pot or operating a mouse to generate these wave generators, this waveform. But for its simplicity and low cost, it's quite remarkable. Welcome back. I hope you found that interesting. I'll just go through the circuit here from left to right. First of all, we have this small board here, and on the board here you have the CMOS 555. There is a PNP transistor which is providing a constant current source for the ramp generation of the 555. This has two advantages. One is that it linearizes the variable control, and when I say linearize, it's an approximate linearization. I didn't really want a strange, unusual, logarithmic-ish shape, and I wanted to try and generate as much as possible a linear dial, and that I managed to achieve relatively easily with a single transistor. It could be more complex than that, and in fact, if you really wanted it completely linear, then you would have to implement this in the form of an integrated circuit op-amp system. But given the application, I needed simplicity. There isn't a green LED here that is being used as a reference, band gap reference of, I think, 1.95 volts. Moving down a bit, well, here's the variable control, and the variable control takes you from 3 to 3. That is, for example, range 2 would be 300 Hertz to 3 kilohertz. Range 1 would be 30 Hertz to 300 Hertz, and range 3 would be 3 kilohertz to 30 kilohertz. The reason why those numbers were identified is the fact that this circuit beyond about 30 kilohertz starts to degrade, and all I really wanted it for was no more than 30 kilohertz, basically audio application and general use. So moving on, we've got here a single transistor that's being used as an inverter. Moving further along, we have the 5015, which is a dual 4-bit shift register configured in a way that generates 8 bits of shifting. That translates into a frequency which is a 16th of the 555. So therefore, for 3 kilohertz output from this circuit, you need to have the 555 running at 48 kilohertz. So the 555 can, on its range 3, run up to quite a high frequency. That would be 480 kilohertz, which is the reason why I put it onto a separate board here, because at those frequencies this type of breadboard would fail miserably. So I moved the oscillator out onto a separate board, and of course for stability. Okay, moving along, we have the output dual op-amp, which is a TLC 272. Okay, moving on to the right hand side of the breadboard is really the business end, and you have 8 resistors here which define the positive half of the wave. The negative half of the wave is a duplication, a copy of the positive half. These resistors are the resistors that define the wave shape, and you change them accordingly. You can remove some resistors, leaving gaps that create one type of waveform. I've even added a diode across one of the resistors to form another wave shape. So there are many permutations that these resistors define. Well, if you don't mind, what we'll do now is move over to the circuit diagram so that we can look at the fine detail of this circuit and see what you make of it. Well, here we are at the schematic of my basic arbitrary waveform generator. A lot of the numbers on the ICs here I've checked a couple of times to make sure they're right, but if there are a couple that might be wrong, please don't shoot me at dawn for it. Starting from the left hand side of this diagram, moving over to the right, we have here at the far left a green LED, which I've used as a band gap reference. I think the voltage at this point here is 1.95. That goes into the variable control, which is a linear 10K pot, and that then drives into a constant current source, which is Q1, the BC559C. That drives the ramp of the 555 capacitor C1, which is a 3.3 nanofarad. For range 2, the first range of this oscillator is from 30 Hz to 300 Hz. The second range, which is the one illustrated here, is from 300 Hz to 3 kilohertz. That translates to a 555 frequency of 4.8 to 48 kilohertz. And range 3 would be from 3 kilohertz to 30 kilohertz, and that would translate into 48 kilohertz to 480 kilohertz. Incidentally, range 1, of course, would be 480 hertz to 4.8 kilohertz. This is a CMOS 555. I chose that because of its ability to perform up to, I think, 1.7 megahertz, so it seemed ideal for the purpose. The supply voltage of this oscillator is plus 9 volts DC. I've taken that from a power supply. It could be operated from a battery, but I quite like the idea of a constant 9 volts DC here. And the current consumption, well, that could be, you could utilize a series regulator like a 7809, 100 milliamps. This whole circuit is not going to draw more than 30 milliamps at the most. You could choose a battery, but of course a battery discharges, and I'm not sure of the stability of the whole of this circuit in relation to a battery discharging. Okay, moving along to the 4015, which is a dual 4-stage static shift register configured in such a way that you're looking at an 8-stage static shift register. The reset has to be pulled up to supply to begin with to clear all the registers so that they operate in the correct synchronized manner, and that's achieved by this circuit here, which pulls up the line via the capacitor C6, via the resistor R20, which is a 10K. When you switch off the power, the capacitor here still has its charge, and the 9 volts effectively drops to the minus volts, leaving the charge here at a negative state. Well, to prevent that negative voltage being applied to the reset pins of the 4015, there is a diode across here, D2 Q2 to catch that negative voltage, so it will never go below minus 0.7. And once that capacitor is discharged, it's ready to be switched on again when you power up again to operate the reset. Moving along, we have within the 4015, the output, the last stage, effectively goes into the D input of the first stage, but it has to be inverted. And what I've done here, I've put a little transistor, the Q2, which is the BC549C, operating as an inverter, and that goes into the D of the first stage, and the input of the base comes is derived from the output of the last stage. You have here around the 4015 a collection of 8 resistors. This is the business end. The resistors go from R6 to R9 and then from R10 to R11. You can see their asterisks here, and that relates to this table here. They are the programming aspect of this oscillator. The arbitrary structure is derived via these resistors, and on some occasions, in some waveforms, these resistors will have different values, and in other configurations some resistors might be omitted, and in others you can add a diode. The one thing you can't do is have 0 ohms across. In fact, actually anything less than 22k, you can't actually have a short circuit across these resistors, a short circuit there and a short circuit there, because you would effectively put an output of one register connected to directly to the output of another register within the 4015. So if you're going to make a connection, always make sure that there is a resistor in here and the value is not less than 22k. If you quickly look at the table here, you can see that it's either open or nothing less than 22k. So that is the business end, and that is how you program it. It's in 2 groups of 4, and each group of 4 relates to each 4 stage of the 4015 with a common connection here, and that is the output. And the output is taken via C4, which is a 1 microfarad capacitor, so it's AC coupled, into a high impedance of, you've got 470k resistor here, into the first op-amp. The first op-amp is referenced to a supply rail splitter. So I referred to the negative here, but that is not the 0 volts as described at this pin here. The output here is actually connected to the half rail connection here. And you've got this from 9 volts to the negative, you've got a rail splitter at half, so you've got 4.5 volts DC here, and that's connected to the positive terminal of the first op-amp. The first op-amp is below unity gain. If you look at the negative feedback of this, you can see that I've got 180k there with a 470k input, so you've got approximately a 0.5 gain value at DC. Across the R17 is the all-important integrating capacitor, and if you want a staircase output, that capacitor is omitted, although as we noticed on the waveform, the traces, there's a little residual switching noise, and so you can, even with a staircase trace, you probably need a very small amount of capacitance in there, maybe 10 puff in there, just to eliminate those little noisy glitches that were evident on the traces. And so if you really want a good smooth sine wave or a good smooth triangular wave or whatever, you do need an integrating capacitor here. This is effectively a low-pass filter. The value that I used was 820 puff. This capacitor here is also related to the frequency in which the generator here is producing. So the higher the frequency, the smaller the capacitor here. The lower the frequency, the higher the capacitor is here. But you can derive an optimum at mid-range. So you've got 3 ranges here, and for each range you could have a capacitor that is set approximately to halfway in that range, so that the waveform would move to deterioration at either end of the dial, but not enough to be noticeable. The output of this first op-amp goes into a level control here, which is a 10k linear control here, and that is terminated at 0 volts. That is this 0 volts, that is a half rail 0 volts, which is here. And this last op-amp is just simply a buffer. I chose this op-amp, which is a TLC 272, simply because it offers a very good drive ability here on its output. I actually preferred the TL072. The 072 offers an improved slew rate, but because I'm not using a gain feature within these 2 op-amps, even the TLC 272 is operating at its maximum bandwidth. And even if I apply a square wave at 30 kilohertz, the rise and fall time is sharp enough to offer a good rise time and fall time. I'll just jump back to the reference. I noticed that I mentioned that it's 1.95 volts DC reference voltage. That is of course with reference to the plus 9 volts here. So the reference voltage would be minus 1.95, or approximately 7 volts DC at this point here. I think that's more or less it. You've got here a table which is effectively over 3 wave traces. The first one was the triangle wave, the next one was the sine wave, and the last one was a odd step differential wave. And you can see that the values for the triangular wave actually is all the same value, 22k, and that produces those nice equidistant in time and voltage steps. You've got here a sine wave. Well, obviously you've got a contouring resistance value from 100k through to 22k, going back up to 100k. And on the last one, which is the odd stop differential wave, you've only got 2 resistors in the first bank, which is R6 and R7, and you've only got 2 resistors in the second bank, which is R12 and R13, which are 22k. The others are actually open circuit. I think that's more or less it concluding. It's a little complicated, but I've enjoyed exploring it. How can this circuit be improved? I can think of a couple of things. One is the op-amp pair on the output. I chose this op-amp because I had it in stock, but I'm sure out there are many op-amps that would suit this application better. Secondly, voltage offset on the output. It'd be nice to include a voltage offset here, and it can be done, I would imagine, relatively easy by having a potential divider at this point here to lift or reduce the DC output with reference to the signal. So that could be an addition. The other thing is the power supply. This is operating from the mains and a voltage regulator. I would probably try attempt to improve this by using a battery pack with one of those little inverter boards, 9-volt inverter boards, and see how this performs with that configuration. The bit that concerns me with that, and the bit that I like about this, is that there is no high frequency component interference on the supply line here. If you go to one of those little inverter boards, there is a high frequency component on the 9 volts, and you might have to include a little inductor, resistive dropper or whatever, to filter out those high frequency components. But sometimes they're hard to get rid of because they're in common mode, and you need quite a good filtering system to achieve that. And as this is an oscillator, I wouldn't like those high frequency components interfering with the oscillation of this system. So that's an area that needs to be explored. Other than that, quite possibly the 30 hertz to 30 kilohertz is a bit limiting, and I probably would like to explore a higher frequency option, maybe 10 kilohertz to 100 kilohertz, but bearing in mind that the driving oscillator would always need to be 16 times that. So you're looking at maybe 1.6 megs oscillator here, a 555 running at 1.6 megs is probably a little tricky affair. That's about it. I can't think of anything else. Maybe you can. Maybe you can give me feedback how this can be improved. This is Beamer signing out for now.